Have you ever really thought about the fabric you're wearing right now? I mean, how did it go from just a bunch of threads to a solid piece of cloth? Well, behind every textile, there's this powerful, rhythmic process, a hidden mechanism that literally slams each thread into place with incredible force and precision. That, right there, is the heartbeat of the loom, and we're about to unpack exactly how it works. Just look at this. This is the moment of creation in weaving. It really is like a heartbeat, or this constant, driving drumbeat. It's a series of perfectly timed impacts that gives life to the fabric, turning all those loose threads into the strong, stable textiles we use every single day. And this powerful motion, it's called the beat-up.
So what exactly is it? Okay, the beat-up is the third of three main things that have to happen to weave anything. Basically, after a horizontal thread, that's the weft, gets passed through all the vertical threads, something has to come along and push it super tightly against the fabric that's already there. That big push, that's the beat-up. And it uses a tool that looks kind of like a giant comb, called a reed, to press that new thread right into the edge of the cloth, which is called the fell.
But how does this powerful pushing motion actually happen? I mean, what makes it go? To understand that, we've got to look at the anatomy of the machine itself, and you'll see it's a really ingenious and kind of deceptively simple piece of mechanical engineering. Okay, this right here is the standard crank-driven beat-up mechanism. At first glance, yeah, it might look a little complicated, but the principle behind it is probably really familiar. It's a lot like the driving wheel of an old steam train or even a piston in an engine. You're just converting a simple rotation into a really powerful back-and-forth motion. So let's break down the key players that make this whole thing work. So you've got three main parts here, and they're all working together in perfect sync. It all starts with the crankshaft. You can think of that as the engine, providing the constant spinning power. That rotation then pushes and pulls the slissy sword, which is this long arm that pivots at the bottom. This is what turns that spin into a powerful sweeping forward arc. And right at the front of that arc is the reed, the comb we talked about that actually makes contact with the thread and delivers that final forceful push. Now, here's where it gets really interesting. Not all fabrics are made with the same rhythm. Nope. Depending on how dense or how tough you need that material to be, you might need a totally different kind of beat-up. This brings us to the difference between a single and a double beat-up. The difference is actually pretty straightforward, but man, it has a huge impact. A single beat-up, which is what you'll find for most common fabrics, gives one push for every new thread. Simple enough. But a double beat-up, that delivers two powerful pushes for each and every thread. And the result? You can create incredibly compact and dense fabrics, like the heavy-duty canvas you'd use for tents or boat sails. So how on earth do you get two beats from just one spin of the crankshaft? Well, this is just some really clever engineering. They add an extra knuckle joint into the connecting arm. So as the crankshaft makes one single turn, this clever little joint bends and then snaps straight, twice. And each time it snaps into place, bam, it delivers a sharp, powerful beat. So here's the takeaway. One thread goes in, but it gets hit with two impacts, packing it in there super, super tight. So, we know it's a powerful motion, but making it work perfectly at high speeds, well, that's a serious physics problem. It becomes this delicate balancing act between speed, force, and, the loom not shaking itself to pieces. To manage this balancing act, engineers use a really important metric called the Slangy eccentricity ratio, or just SER. Now, don't let the name scare you. It's just the ratio of the crank's radius to the length of that big connecting arm. All it's really telling us is how uneven the rhythm is. A high SER makes the slangy swing forward really fast for a powerful beat, but then it swings back more slowly. And that slower return trip is actually critical. It gives the shuttle more time to pass the next thread through.
And this just perfectly illustrates the trade-off that engineers are always dealing with. On the one hand, a high SER is great. It gives you more time for weaving and a much stronger beat-up. But on the other hand, all that rapid acceleration and deceleration puts immense stress on all the loom's parts. It causes way more vibration, more wear and tear, and it means you need a much more robust, and yeah, more expensive, machine to handle it all.
This leads to a fascinating question. We've been talking all about making the beat-up more and more effective. But is there such a thing as it being too powerful? Oh yeah, there definitely is. You get a condition called bumping. This is what happens when the beat-up is so forceful that it shoves the edge of the fabric so hard that the vertical warp threads actually go slack for a split second.
Now, you'd think more force is better, but it's the total opposite here. Pushing on those slack threads is like trying to push a rope. It's completely ineffective. It actually reduces how tightly the fabric gets packed. Okay, so the challenge is pretty clear, right? Knowing all these limits, stress, vibration, that whole bumping issue, how do engineers actually make looms faster? Let's jump into our final section and see how modern material science is totally revolutionizing this age-old mechanism.
The difference that just changing the material makes is, well, it's staggering. Check this out. At 180 RPM, a traditional wooden sleigh creates a massive 1,160 newtons of force during that beat up. But by swapping it out with a much lighter aluminum design, that force plummets to just 300 newtons. The speed is exactly the same, but the stress on the machine is just a fraction of what it was. And you can see that evolution right here. On the left, you've got the classic, heavy wooden sleigh. And on the right, the modern, lightweight, and highly engineered aluminum version. It's the same core idea, but a complete world of difference in terms of performance. Let's just put a number on that. By switching from wood to aluminum, the total weight of that whole moving sleigh assembly was slashed from 80 kilograms all the way down to just 14. That is a mind-boggling reduction of 82.5%. So here's the bottom line. Making the swimweigh lighter means there's less mass to throw back and forth, and that directly translates to less force, less vibration, and less wear and tear on the machine. The ultimate result? The loom can run significantly faster, which dramatically increases productivity, all without shaking itself to pieces. And, this quote from the source material really just frames the entire engineering challenge perfectly. The shuttle loom is essential for making clothes, but its one major, glaring drawback has always been its low speed. The material innovations we just looked at are the direct answer to that fundamental problem. So, the next time you pick up a piece of clothing, just remember that incredible dance of physics and engineering that brought it to life. That constant, powerful heartbeat of the loom. And it really makes you wonder, doesn't it? What other hidden forces are busy shaping the everyday objects all around us?